Hello learner, welcome once again to Manifested Online Classes. My name is James Kenyani. In our today's lesson, we are going to look at application of area under curve. Application of area approximation. Application of area approximation. So it is application of area application. So somebody would ask himself, why learn all these when you cannot apply it anywhere? So in our today's lesson, we are going to apply our lesson in what we call kinematics. In kinematics, it involves the trajectories of points, lines, or other geometrical objects. And this will be clearly seen when we talk about speed and time. Speed, time graphs. So there is a new word there, kinematics. So to enable the learner to understand how to use the knowledge on area approximation in speed time graphs. So kinematics is the trajectory of points, lines, or geometric So to make the task simpler, we shall just go to the time, speed time graphs. So learner, looking on figure A, we start with figure A. You can see on the horizontal axis, there is time in seconds, and on the vertical axis, there is speed in meters per second. At 0 seconds, the speed of that car, it is talking about the speed of a car. At 0 seconds, the speed of that car, 40 meters per second. At 8 seconds, 40 meters per second. It doesn't change the speed. It doesn't change the speed. It doesn't change the speed. So you can say in figure A, the speed of the car is constant. When the speed is constant, we say there is no acceleration. There is no increase in speed. In figure A, the speed of the car is constant. The acceleration, there is no acceleration. So when you talk of acceleration, it is change in speed. Acceleration is change in speed. There is no change in speed. You might want to know the distance traveled. We know that in this, the distance will be equal to the area in the graph. This whole area will be the distance, which is given by speed times time. You see, I'm applying that information. When I get the area, that area, the distance traveled will be the area in the graph times this. It will be the speed times time, which is the area in the graph. This is equal to 40 meters per second times 8 seconds. So the vehicle travels how many meters, Lana? The vehicle travels 320. That 320 is actually the area in that graph, that dotted or shaded area. That is one of the application you get under area under curves. We go to figure B. In figure B, you see a sloping line. In figure B, the vehicle changes speed from 0 seconds to 8 seconds. When there is a change in speed, we say there is an acceleration. Therefore, there is an acceleration, into brackets, constant. It is constant acceleration because of the straight line. It doesn't change. And acceleration is equal to change in speed divided by time. Change in speed divided by time. In the first case, we realized there was no acceleration. The speed was constant. That's why the curve was parallel to the x-axis. Constant, no change. No change, same speed. So we shall come and get here what, Lana? The change in speed from 0, it is at 10. At 8 seconds, it is at 40. So the change in speed within that time will be 40 meters per second, subtract 10 meters per second. Subtract 10 meters per second, you divide by 8 seconds. Acceleration is equal to change in speed over time. So I'll come here and work out 30 meters per second divided by 8 seconds. 8 seconds. So you'll simplify. 2 goes there. 15. 2 goes there. 2 goes there. So 2 goes there. 15, 2 goes there, 4. So it is 15 over 4. 15 over 4, which will give me 3.75 meters per second per second. Per second per second, because there is a second down there. This works to 3.75 meters per second squared. You put there minus 2 because there is second. So that is the acceleration. The speed changes by a magnitude of 30 within 8 seconds. So the acceleration is given by that. So we learned that the area under speed time graphs gives the distance. When that curve, that line is straight, there is no change in speed. But when you see it sloping, there is a positive change in speed. Like if you boarded a matatu today, you saw the driver accelerating the vehicle. It started from 0 and moved to a speed. Notice that also when the driver is stopping the vehicle, there is a deceleration, a negative change in speed. So if it was a negative change in speed, it will slope that way. But since there is a positive change in speed, acceleration, it goes that way. So when somebody is braking a vehicle down, it will change from a higher speed to a lower speed. So that one is called deceleration, but here we have acceleration. So to continue, we had not finished there. So the area in B, I can just use this space. Area in B will also be equal to distance. Area in B will be equal to distance, and there is a trapezium. It is a trapezium, so it will be given by a half sum of the parallel sides 10 meters per second plus 40 meters per second times 8 seconds times 8 seconds times 8 seconds. Just as we got there, distance is equal to speed times time. So when I'm getting this, I'm getting the speed. So 2 goes there, 1, 2 goes there, 4. So this was supposed to be 40 meters per second. So 30, 10 plus, divide by 2, since it is a trapezium. So I already, so I didn't need this. So this was 10, and that is 40. 10 plus 40 is 50. 10 plus 40 is 50, because we have here 40, and that is 10. 40, and that is 10. So these 2 cancels with the 8, we get 4. We get 4. So it's going to be 50 times 4, and we get how many meters? We actually get the 200 meters in B. We get the 200 meters in B. We get the 200 meters are traveled in that speed time graph. So learner, know that this is where we use the speed time graph. So we can get the area in that graph, and it will be equivalent to the distance. Whenever there is such a thing, that is an acceleration. Whenever the speed would be dropping down, that is a deceleration, like when the driver is braking the vehicle. So with that, there'll be a short assignment. So quickly going through the question. Number 1, a car traveled at a constant speed for 8 seconds, covering a distance of 48 meters. Then it was uniformly retarded, decelerated, and brought to rest in 3 seconds. Draw a speed time graph for the 11 seconds and find the distance traveled. Number 2, a body starts from rest and accelerates at 3 meters per second squared for 4 seconds. It then travels with a maximum velocity for a further 3 seconds and finally comes to rest with a uniform retardation after another 5 seconds. find graphically the distance traveled and the average velocity for the whole period. So go through that and it will give you a benefit from the speed time graphs. Thank you very much, and let's meet in the next lesson. Bye-bye.